Next, all magnets are what we call bipolar. Bi means two. There's always two poles. In electricity, it was positive and negative. For magnetism, it's north and south. And that's because traditionally, what were magnets used for? They were first used for navigation as compasses. And the north pole of a compass was defined as the direction that a needle, a magnetized piece of iron or steel, would point. And all steel is it's just iron mixed with a few other elements, carbon, and depending on the type of alloy, like stainless steel, you might have cobalt, whatever, mixed in there. So anyway, it'll point. The north end of a magnet is defined as pointing to the north pole of the Earth. So anyway, all magnets are bipolar. What does that mean? As far as we know, you cannot have a magnetic monopole. If you take a bar magnet and chop it in half, you don't just have a north pole and a south pole. You get two baby bar magnets. If you chop those in half again, you get four baby bar magnets, etc. And just like electricity, so what's kind of nice about physics is as you start to understand how nature works, there's patterns. Opposites attract, and likes will what? Repel there, right? So what's nice about that is it's a natural phenomena and trying to understand that. So one thing that's tricky about magnetic bipoles versus monopoles is getting something to float. So because you always have a magnetic bipole, a north-north and a south-south, to get like a train or a car to float, so this is a little duct tape model we made here of a maglev train here. Let's say I have north poles of magnets facing up on the track. So to get the train to float, I have to have north poles on the bottom side to face down, right? But naturally, so the problem with this is it naturally wants to then attract the south pole and flip this thing over. You see that? So understanding that bipoles are natural and monopoles are not natural is important if you want to design a system using magnetic fields to float a train, etc.